what's coming next. And so the test has been moved to Wednesday. So I will again post an announcement. Okay, so next year we have Einstein, 1915. Okay, so before that, he came up with a special relativity that says, for example, if you have a spacecraft going at the speed of light, leaving Earth and coming back, the people in the spacecraft will not have aged relative to the Earth, and people on Earth will have aged, right? But that's special relativity. Then he tackled general relativity. So that was the movie, I think it's from Nova. It was a very nice movie I showed you last time. And that was in 1915, right? 1915, general relativity. And basically he says that there is no such thing as the force of gravity. Okay, it's just an approximation. That why is the Earth orbiting the Sun? It's just because it's been trapped in one of the rad space time. So it means like imagine the Sun and it's on the trampoline, right? So space is in 3D, but you can imagine that it's in 2D. So the Sun is so heavy, it's going to curve the trampoline, and the Earth is trapped around. So that's the idea of general relativity. It's simplified a lot, and there is like a demo that someone did. Let's do it quick. Gravity visualize.
Relativity, the explanation for gravity.
Okay, so here we go again with the
so you put mass in a place in space, warp space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike short.
and so what he used a rubber sheet, right, to for students to visualize the space fabric. So it's 3D, but this is just to visualize.
You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like $20, maybe less. And so you put matter and it works space-time. And so if I have another object, it also works space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects work space-time, feel that curvature, move accordingly.
So you see, according to Einstein, there is no such thing as the force of gravity, right? It's just space, the fabric of space that's being wrapped. So it's being pushed by the fabric. So why is it that we cannot escape Earth? It's not because there is a weight pulling us, it's just space itself pushing us toward the Earth. Like this. Did you see? They had two mass and they are being pushed together because space is a fabric.
More mass.
Right here.
Yeah, more mass is going to bend space-time more. And so if you have a object here, they're going to respond to that, right? And so you put something there, that's attracted. Now, in reality, that big mass would feel the warping of space-time by the bar too, right? We move a little bit. We usually ignore that. You know, the Earth makes the sun move a little bit, so it's so small we can ignore it. The moon makes the Earth kind of wobble around a point 3/4 away from the center of the Earth. We usually don't account for that when we're looking at satellite push. Well, instead of just let it go one, what if I do a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only likes clockwise, or whether it's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. This one had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way.
Okay, so if you want, you find this video on YouTube. So, conclusion, Newton gravity, law of gravitation, even though, of course, he was a genius, it's just an approximation. But you don't want to go in all those computations. If you need to send someone on the moon, Newton will do it, okay? You don't have to make it complicated. So if you're interested, it's great. You can watch this. So we end up here, right? So we have Einstein. So we started here with the Greek, the geocentric system. Then you have Tycho Brahe. I don't know if there was a question like that, but he was able to observe the motion of Mars as seen from the Earth. He hired Kepler, right? He was playing a little game with him, and Kepler changed the frame of reference, and he described the motion of Mars relative to the Earth, and he came up. So if I ask you who came up with those three planetary motion laws, that's Kepler, right? First law, all the planets go around the sun following ellipses. Second law, equal area, equal time. So this slow, slow. And the third law, there is a relationship between the distance between the sun and the planet and how long it takes, right? And to do that, he had to steal the data, which I think very interesting, right? He had to stick in the house and took all this observational data. So that's very cool. And then you have Galileo. He came up with the first refracting telescope, so two lenses, right? And actually, he didn't give credit where credit belonged. It was an optician from Holland who made it for the first time, but he improved it. And he got a tenure because he sold his invention to the Prince of Venice. And then came Isaac Newton. So if I ask you, what did he do with the telescope? He built the first reflecting telescope, so with a mirror, right? Not with a lens. It's better. And then came Einstein, 1915, with the general relativity. So many times when there is a new theory, you have to wait for the person to die, and decades later they say, oh, he was right, like Giordano Bruno. Okay, so if I ask you, what happened to him? He was burned at stake, but he came up with general relativity in 1915, and they were able to prove it in 1919. So in his lifetime, and that's how he became a rock star. Yeah, as much as Charlie Chaplin. So yeah, so he was a rock star. So what they did this very famous experiment. I have another picture, but basically what happened? Oh, someone remind me, yesterday there was an eclipse, partial eclipse. I went to bed, but did you see it? If you saw it, see, when you want to boost your resume, it tell you, say, oh, I'm following all the eclipses and I've seen this one that day. It's very nice. So 2 people here saw it yesterday. That was great, right? So that's very nice. And if you do it for real, of course, they will know that you know what you're talking about. So anyway, so it depends on the place on Earth. So some places, like from here, you only saw like a partial eclipse. So that means that the moon was in front of the sun, but only partially. So it means you are just missing a bite of the moon. But in some other places, you have a total eclipse. So that happened in 1990 in an island. I think close to Africa, I think it was. Let's see. Where was it? Eclipse 1919. Island of Principe. It's west coast of Africa. So Lord Edington, who was British, very famous astrophysicist, okay, he organized everything, he got the money, and he went to this island and he was able to observe that eclipse. So what's so special about this eclipse is that you see the Earth is here, this is the sun, right? And the sun was shielded by this moon, right? It's a total eclipse. So here you have a star, okay, behind the sun, okay, relative to us. So you're not supposed to see it. First of all, you're not supposed to see it because in that season, you see the sun is here, so you cannot see it. Of course. Plus, you cannot see it because it's behind the sun. However, because the space-time is wrapped, is curved, right? So because the sun is curving the fabric of space-time, what happened is that the light coming from the star here, it's going to be curved here, right? It's curving because of the presence of the sun. So it's very much like the video I show you. So here you have a big mass. So you have a curve, right? The fabric of space-time is curved, and the light is making like a turn here because it's trapped into the curve, which means that instead to see the star here, you're gonna see it here. So it's like an apparent location, right? So it's like the light goes this way, it's being curved, but from our perspective, we think that the light goes in a straight line. So we're gonna see the light here. So that was the proof of general relativity. That was the proof that space-time is curved. And that was the revolution because, of course, Einstein at that time became very famous, right? So after that, okay, so they have done similar experiments. So in that case, you have the same thing. So here you have a white dwarf. So that was done in 2017. So you have a white dwarf, light. No, that's it. It's here. You have a star here. And because the white dwarf is the remnant of a star that is very heavy. So you see it's curving space-time, and the light is going to go this way, so you're going to see the star there. Okay? So that was a big revolution at the time. I don't know if I have more eclipse. Okay, maybe this one is good also. So this is the Earth, that's the sun, and light coming from that star is being trapped in the curve, and you're gonna see the star here. So it's like a mirage. That's how mirage works, right? When sometimes you go on the highway, you are driving, it's very hot. It seems to you that you have water in front of you, but it's just a mirage. That's because light from the sun or from the sky, it's blue, right, goes down to Earth and it's been curved like this, right? So you have the blue here of the sky, and because it's going through the atmosphere, light is curved, and our brain thinks that light goes along a straight line, and we see the blue on the highway, even though there is no water. Same thing when you are walking in a desert, and it's very hot, you have mirage, right? You think it's water, but actually it's just the apparent image of the sky. So same thing here. So that was a big breakthrough. Let's see if I didn't forget anything. Any question? So that was 1990. Lord Eddington, I will get back to him. Okay, so then 1920, another breakthrough in astronomy that became astrophysics. That was Edwin Hubble, 1920, and he's the one, through observations, who understood that the universe is not static. They were not sure at the time. Is it moving? Is it expanding? Or is it static? Or maybe it's going to collapse because gravity, you're going to have a big crunch, right? So they were not sure, and he was able to show that actually the universe is expanding. So you can imagine the universe as being in 2D, even though it's 3D, but very hard to imagine in 3D, unless you imagine like a bread. Imagine like you have a bread with raisins inside, and once the bread is gonna inflate, all those little raisins are moving away from each other, so that will be 3D. But if you imagine in 2D, you see after the Big Bang, all those galaxies are moving away from each other, right? And how he did that? He did that because he was observing galaxies. So first of all, he understood that we have many other galaxies, okay, instead of our Milky Way. So we have our Milky Way, but you could see like nebulae. So people thought they were nebulae, but actually they were galaxies. So that he's the one who understood that. But the galaxies are moving away from each other. So how did he do it? It's something called the Doppler effect. So I don't know if you know the Doppler effect, but if something goes really fast, like this, past you, like maybe the bikers, right? The crazy bikers that go really, really fast. It's not, what do you think, what noise you're gonna hear? Do you hear eh? Do you hear meow? Oh, do you hear which one? The second one, right? Meow. Why? Because the sound is shifted. So the frequency will be changed. So when it's coming towards you, it's going to be high frequency. Away from you, it's going to be low frequency. Right? It's called the red shift. Yeah. So towards you, higher frequency. Away from you, lower frequency. And that's how the police officer, they can tell how fast you go. They have a special gun, right? So they sound like ultrasound. The ultrasound will reflect from your car, and because there is a shift in frequency, they know how fast you are going. So it's because of the Doppler effect, right? So turns out you also have a Doppler effect for light. So it means that if a source of light is coming towards you, it's going to be blue shifted. So here, that's Doppler effect for sound. Okay, so you see, this is a sound. It's a wave. You have the crest, right? If it's coming towards you, it's going to be piling up. So you're going to hear a higher pitch from your frame of reference, and if it's moving away, lower pitch, right? Yeah, higher pitch, lower pitch. But it works exactly the same for light. So light, you see, you have light when you take the white light. Remember, you have all the rainbow colors, right? You have red and yellow and green and blue. Red has a lower frequency and blue has a higher frequency. The way you can remember is that higher frequency, higher energy, but it is for us. So blue is close to UV, which is not so great, and then UV, X-ray, gamma rays. On the other side, you have red. Red has a low frequency, and then you have infrared, and then you have microwave, and then you have radio wave, which are not problematic. Okay, so this is low frequency, and this is high frequency. So if you look at galaxies, for example, through a prism, you're going to see those colors here, right? And you're going to see that spectrum. If the galaxy is coming toward us, it's going to be blue. The galaxy will appear blue. I'm simplifying. If the galaxy is moving away from us, the galaxy will appear red. Do you understand? So let's see. I had a redshift, a video maybe. see redshifted, so it works also for stars or even planets. Okay, if the planet or the star is moving toward us, so higher pitch, it's going to be blue. Even though it does not make sense, but it's the light that is shifted toward the blue. If it's moving away, it's going to be redshifted. Okay, so typical question, galaxy moving away, it's going to be redshifted, toward, it's going to be blue shifted. So when he started to observe all the galaxies appear redshifted, which means that all the galaxies around us, okay, not in our local group because everything is glued together, but if you look like farther and farther away, everything seems to move away from each other. So it was redshifted, which means that the universe is expanding. So the galaxies are not expanding, but it's a fabric of space, right? It's expandable that is expanding. And that was a big breakthrough. So let's see if I have a redshift movie here.
Stars are made up of a number of different elements. The Sun is composed of about 73% hydrogen, 25% helium, 0.8% oxygen, and 0.36% carbon, plus smaller amounts of other elements. Each of these elements absorbs certain wavelengths of light. White light is made up of the full spectrum of wavelengths. But the presence of elements such as hydrogen and helium results in black lines in the spectrum. These are the spectral lines for hydrogen, and the black lines appear at the particular wavelengths that are absorbed by hydrogen. Here are the spectral lines for the Sun. By analyzing these lines, scientists can tell what elements make up the Sun. And spectral lines can also be used to investigate what elements make up stars and distant galaxies. Scientists can also use spectral lines to work out whether a galaxy like this is moving towards the Earth or away from the Earth. Let's compare two sets of spectral lines for this galaxy as we expect them to appear. The positions of the spectral lines are based on the absorption lines for various elements as they have been measured in laboratories on Earth. If the galaxy was moving towards an observer on the Earth, the spectral lines would shift to the blue end of the spectrum. This is known as a blue shift. If the galaxy was moving away from an observer on the Earth, the spectral lines would shift to the red end of the spectrum. This is known as a redshift. The further the spectral lines are shifted, the faster the galaxy is moving away from the observer, and the further away the galaxy is from the Earth. Astronomers such as Edwin and Hubble measured the spectral lines of hundreds of galaxies in the visible universe and found that most galaxies display a redshift. This led to the conclusion that the galaxies were moving away from the Earth and that the universe must be expanding.
It's a very nice video, right? It explained very well. And for the test, if you pay attention in class, it's an easy class, okay? If you don't disappear for 10 minutes or whatever, it's very easy to get an A. So just pay attention, and that's it. It's very interesting too. Okay, so that just a student sent me that. I don't know if you know the Big Bang Theory. It was a show. Okay, my colleagues didn't like it because they make fun of physicists. They describe them as weirdos, but maybe it's true. I don't know. I'm sure I'm kind of weird. But in this episode, he describes the Doppler effect. So I'm gonna talk fast.
I don't care if anybody gets it. I'm going as the Doppler effect. No, it's not about you. I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out prizes for best costume. Most frightening, most authentic, most accurate visualization of the scientific principle.
Oh, Sheldon, I'm sorry.
Sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor and Peter Pan. That's so cute.
Actually, Penny's right here. I got a handful of pixie dust with your name on it.
No, you don't. hate
I hate
what
what
Sheldon's
Sheldon's
supposed
supposed
to
to
be.
be.
Oh, he's the doppler. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Did you hear that? That's exactly the definition. And apparently the actor doesn't understand anything, but he was very good at memorizing the exact definition.
Caused by relative motion between the source of the wave and the doppler. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now. The
Doppler effect.
All right, I got a shower.
Shower, you guys
Make
make
yourselves
yourselves comfortable. Okay. So you can watch the answer on your own, but it's exactly that. If there is a relative motion between the observer and the source of sound, you're going to have a shift in frequency. So if the source is coming towards you, higher frequency, away from you, lower frequency. And it works with light. So I think in my frame of reference, that was a very good episode. So here you have, let's see, the source can be reached. Oh, did it? Oh, they remove. Cannot go here. Start. So here nothing. So it's a source of light. It's green. Nothing special. Right? So the observer can be here, and it's gonna see, the observer is gonna see green. But now, if the source is moving, so we're gonna make the source move, okay? And what's gonna happen? Start. You see, if you are here, the source is coming towards you. You're gonna see blue. You think the source is blue. If you are behind, okay, and it's moving away from you, it's gonna be red. So moving away, red shifted, toward you, blue shifted. So yeah. It depends again on your frame of reference. So that was a big breakthrough, and he has also an interesting history because his parents wanted him to study law, but he didn't like it. I don't know, at the time you have to take the LSAT, but he didn't like it, so he did a little bit to please his parents, but then he shifted. So anyway, so that's the idea, is that the universe is expanding. And one of the next big breakthrough, it's going to be what we call the cosmic microwave background. So if the universe started with a big bang, all the light from the big bang, right, started to escape at some point. So it will be permeating like all over the universe, this light from the Big Bang. But because the universe is expanding, you will expect that light to be stretched out. So the light from the Big Bang, maybe it was in UVs, okay, or visible, but by the time it gets to us, right, now, 14 billion years later, it should have been stretched. That's what we call the cosmic microwave background. So I will explain that. So I have a very short video here. I'm not going to show you, it's not that short, but I'm not going to show you everything. But I will keep the for another topic. No, it's long, so we're not going to watch the whole thing.
Ever since people started thinking about the structure of the universe, they have sought to plumb its depths. But it took an American astronomer to solve the puzzle concerning its limits, if any.
So I don't know if you watch a picture of him or video, he always has a pipe. So that was before smoking was
Edwin Hubble came at the end of a long line of scientists, some who paid their lives for their curiosity. In 1600, the Holy Inquisition sentenced Cardinal Bruno to death, among other things because he had declared the universe to be without limits and home to an infinite number of worlds. 87 years later, Isaac Newton provided theoretical support for the worldview of Nicholas Copernicus, according to whom the Sun, and not the Earth, was at the centre of all things. In evidence, Newton pointed to the attractive force of the Sun, which keeps the planets in their orbits. In so doing, he shook the view taken by the Church to its foundations. But in other ways, he provided the Church with intellectual support. Newton had observed that many of the so-called fixed stars did in fact move. According to his laws of motion, however, everything would have to be in motion, including heavenly bodies still unseen. Consequently, the universe could not have any limits. This explanation by Newton now seems to go down well in Rome. After all, it accorded with the idea that God had created the universe in his own image. If God was eternal, then so must the universe be. But how did the universe come about in the first place? And why are the stars so far apart when gravity should be pulling them together? Newton did not have the instruments to answer these questions, but in the next 250 years, great progress was made. Using a huge telescope he had built himself, William Herschel discovered the planet Uranus in 1785. While observing the heavens, Herschel also kept coming across bright points surrounded by a sort of fuzz. At first he thought they were stars surrounded by clouds of gas and dust. In 1845, the Irish astronomer William Parsons, the Earl of Ross, completed his reflecting telescope, which he called Leviathan. Weighing 10 tons, it was the most powerful telescope of its day. With it, Ross recognized for the first time that many of these nebulae, as they were called, were spiral in form. He did not know that they were other galaxies. His drawing is amazingly detailed, as can be seen by comparing it with a photograph. But while more and more spiral nebulae were discovered, there was still no model to explain what they actually were. This man was to provide the answer. Edwin Hubble was born in Marshfield, Missouri, on the 20th of November 1889, the son of an insurance salesman. At an early stage, he developed a keen interest in astronomy, and Jules Verne's From the Earth to the Moon was one of his favourite stories. His grandfather had built a telescope for himself, and young Edwin spent many a night using it to observe the heavens. His father's business brought the family to Wheaton, a suburb of Chicago. Edwin was allowed to spend the night of the 23rd of June 1899 with his friend Sam in the open air to watch the eclipse of the moon. A magnificent spectacle to the two boys. Because of his grade at school, Edwin won a scholarship to the University of Chicago, where he studied mathematics and astronomy, besides excelling in college sport. But although his passion was astronomy, he followed his father's wishes, and in 1910 went to England to study law at Oxford. He was neither particularly interested nor particularly successful. 3 years later, he returned and continued his astronomy studies at the Yerkes Observatory in Chicago in 1914. In his doctoral dissertation, Hubble hypothesized that the spiral nebulae were independent galaxies, far beyond our own Milky Way. But in order to prove this, he had somehow to measure their distance. For this purpose, astronomers used a class of stars whose brightness varies periodically, known as Cepheid variables. They have proved a useful astronomical measuring rod. To track down some of these Cepheid variables, Hubble went in 1919 to the Hale Observatory on Mount Wilson near Pasadena, where the world's largest telescope had been brought into operation the year before. A reflector, its mirror was 100 inches or 254 centimeters in diameter. Hubble devoted his attention first to the Andromeda Nebula, the only galaxy visible with the naked eye from the Northern Hemisphere. He hoped to find Cepheid variables there. And indeed, after years of intensive observation, he found some in the middle of the Andromeda Galaxy. He captured the result on photographic plates. With the aid of the Cepheids, he now succeeded in determining the distance of the Andromeda Nebula from the Earth, a good 800,000 light-years. This enormous distance is about 8 times the diameter of the Milky Way, so the Andromeda Nebula cannot possibly be part of our known galaxy. Although we now know that the Andromeda Nebula is in fact 3 times more distant still, 2.4 million light years, Hubble had already proved that there were galaxies beyond our own Milky Way. Once it was clear that there must be independent galaxies, Hubble and his assistants Milton and Humason set about analyzing their spectra. The lines in a spectrum are what make it unique. They provide astrophysicists with a kind of optical fingerprint, which supplies various pieces of information. Among them, the chemical composition of the source, in this case the galaxies. The two astronomers noticed that the lines were shifted towards the red end of the spectrum, a sign that the galaxies were moving away from the Earth. This redshift derives from the fact that the light is a wave. Visible light ranges from red, with a wavelength of about 700 nanometers, to violet, with a wavelength of 390 nanometers. Waves at the red end are longer. When a cosmic object, a galaxy for example, is receding from the Earth, the waves are stretched. In other words, its spectrum is shifted towards the red end. An approaching body would display a corresponding blue shift. Its waves would be squashed. This phenomenon, known as the Doppler effect, is also observed with sound. It is named after the Austrian physicist Christian Doppler, who noticed that a locomotive steam whistle sounds higher when it is approaching and lower when it is receding. The pitch changes because the sound waves and the sound source are moving. If the source is approaching, the waves are squashed and the shorter waves sound higher. If the train is moving away from us, the waves are stretched, and longer waves sound lower. If this logic is applied to the galaxies, a redshift, in other words, a lengthening of the light waves, means that the galaxy must be receding. Most of the galaxies investigated by Hubble were in fact redshifted, and the more distant they were, the more pronounced the redshift. This means that the most distant galaxies are receding the fastest. This association between distance and velocity has gone down in history as the Hubble effect. It proves that the universe is expanding and that the galaxies are drifting apart, like points on a rubber band when it is stretched. Hubble was even able to back up his discovery with a mathematical formula known as Hubble's law. It states that the velocity of recession, in other words, the speed at which the galaxies are moving apart, increases in proportion to the distance between. Hubble's discovery supports the theory of the Big Bang, the idea that the universe did actually have an origin, a theory in accordance with the creation image of the Christian Church. The Vatican Observatory at Castel Gandolfo was the workplace of the Belgian Jesuit priest Georges Lemaitre, a respected astronomer and an ardent advocate of the Big Bang theory, long before it was given this name. According to Lemaitre, the universe emerged from a primordial atom created by God. He was happy with the idea that the universe was expanding. The astronomer priest sought support for his thesis from one of the most respected scientists of his day, Albert Einstein. However, Einstein favoured the steady state model, a universe with no beginning. When Einstein visited Hubble on Mount Wilson in January 1931, Lemaitre was also present. After they presented their views to Einstein, he admitted that he had been wrong. But there were other scientists who opposed the Big Bang theory. Foremost among them, the British astronomer Sir Fred Hoyle. Hoyle demanded proof of the Big Bang and wanted at least to see its leftovers. Let's see the fossil record of this Big Bang, he joked. In 1948...
Okay, so that will come next. Let's see. What he said in the movie is that if the universe is expanding, so at a constant rate, so expanding at a constant rate, from your point of view, farther you look, faster the galaxy seems to be moving. So there is a relationship between the speed and the distance. So to understand that, here I wrote like a 2D universe, right? That's my 2D universe. And those here are super clusters or clusters of galaxies. So let's say we live in this supercluster. Here we have our local group, and inside we have the Milky Way. And you see, I'm stretching at a constant rate. So what is stretching? It's not the clusters themselves, but it's a space between them. Do you agree? So even though I'm stretching at a constant rate, if you live here, right, after a given time, you're going to have more stretched between here and there than between here and there. So from my perspective, during the same amount of time, okay, this one seems to go faster than that one. Do you understand? Because you have more stretch, right? You have more fabric. The distance is more. But it doesn't mean that it's expanding faster, okay? It's expanding at a constant rate, but from your perspective, further you look, right, the speed will be more, right? So if it is so that journalist or astrophysicist, he made fun, right? He say, ha ha ha, the Big Bang. Okay, so if it is true, it means that when there was a Big Bang, you have the light escaping. This light, I don't know if you can see the little light here escaping from the Big Bang. If the universe is stretching, expanding, you should be able to see that light coming from all directions, right? Because that will be the remnant of the Big Bang. So he made fun of the theory of the Big Bang, and he's the one who called it Big Bang. Why Big Bang? Just to make fun of it, right? So but the term sticks. So the term Big Bang, it was not coined by Edwin Hubble. It was coined by a British astronomer just to make fun of that Big Bang theory. So the next step was to try to look for that fossil light, as he said in the video, right? So if there was a Big Bang, light at some point start to escape after 380,000 years, and that light will be stretched out. And that we expect to see in all directions that fossil light, right? That will be the cosmic microwave background. Right? So he was very passionate, right? If you have a passion, go for it. So then in the 1930s, maybe I will leave that for next time, but you have and sometimes in science or in other domains, things happen by chance. So he was not a physicist, he was an engineer, Jansky, and he was working for the Bell Laboratory. The Bell Laboratory was in Princeton, New Jersey. So it belonged to the telephone company, AT&T. So they have a research lab, and engineers were working for them to get rid of the static. So static was an issue. So that's when the story starts. So I'm going to stop here, but that next step here happened by chance. So remember, you have the test